So it's my pleasure to introduce and to have in our seminar Sahar Diskin from ETH. So Sahar is postdoc there. Before he did PhD in Tel Aviv University with Michael Krivilevich. And Sahar has many great results, and today he will tell us about the recent breakthrough in supercritical sharpness of percolation. Please, Sahar.
Thank you very much. Thank you for the introduction and thank you for having me. So yeah, we're going to talk about supercritical sharpness. And everything I'm going to talk about is joint work with few colleagues here in ETH, but let me introduce them when we get to the theorem. So let me start first with a bit of a background. And so the very basic idea is that suppose we have some graph G with vertex set V and edge set E. And suppose we have some parameter P between 0 and 1. This is a probability parameter. Then we can define the following. So I'm going to write this in a probabilistic type of way, but I will explain in a moment how we usually view this type of stuff. So we can consider the measure of the probability with parameter P on the graph G, which is what we will call a percolation on G with parameter or with probability P. So what does this mean? So this means the following. So for example, suppose that I start with the following graph. So this is my graph G. Let's say it looks like this. So I have this is my graph that I started with. And then for every vertex, for every edge, sorry, I put a coin next to it. And with probability P, I retain it, and with probability 1 minus P, I don't retain it. So after doing this thing, after taking this random subgraph, I will obtain something different. So I still have the same set of vertices. But now say this edge survived, this edge didn't, this edge didn't, this edge survived, and this edge survived. So every edge either survives, retains, or does not. Okay, good. And now, in our world, so we're very familiar with the following object, which is in our world, meaning in random graphs and in combinatorics. So if I take the complete graph with parameter P, so what is this? This is exactly the same as G and P. So this is from the point of view of, let me call it, random graphs. And this was introduced already by Erdos and Rainey. and also by Gilbert in the late 50s. So if I'm not mistaken, 58. Okay, so this is one way to view the world. And usually when we think about random graphs, what we think about is we take some graph, we take its subgraph, and we are interested in the combinatorial properties of this thing, but we are also interested in the connected components of this graph. So what do I mean by connected component? So for example, here, this thing here is a connected component, and this is another connected component. So we are also quite often interested in disconnected components and how they behave. So these are the two things we usually care about when we look at random graphs. So this is the perspective that we're mostly used for. But let me suggest and let me introduce more so, not suggest, it was suggested way before me, a different perspective on this object. So this is, let me title it as percolation on ZD. So this is how it started, at least. On the lattice, the d-dimensional lattice. And we still have the same thing. So we start with the d-dimensional grid. And we do this process, and then some parts remain. Some edges remain, some edges are not. So for example, we can have this. And obviously we still have the nodes and everything.
You
Okay.
percolate here on edges, not on vertices, right? So
Yeah,
retain
it's
edges.
still everything on edges. Yeah, the percolation is still on edges. So I have here the nodes, for example, that they're just isolated. Exactly. Thank you. Okay, and particularly on the lattice or this type of thing. So this was introduced by Broadbent and Hammersley. In 57, and they wanted to, it's tightly related to statistical mechanics and to physics. They wanted to understand, so particularly they were actually interested in if you have a gas mask, what's the probability that, or how does it behave? You have a gas mask, what are the chances that some poisonous gas can pour through? But if you prefer something that's more related to, or hopefully more related to our day-to-day life, so you can think about when you brew coffee. So you have, yeah, let me try a bit my drawing skills. So you have here the grounded coffee. And you have here wherever it goes to, and you pour water. And the question is whether eventually the water will be able to filter through and you will get your filter coffee, which some people really, really like and some people hate, but that's beyond the point right now. But espresso works in the same way, so forget about it for now. And the point is that obviously if the coffee beans, or if the grounded coffee is very, very dense, and there is no space to move in between, we can imagine it as if my P is 0. And then I have no chance to go through. But if my probability, if there is some space in between, then the water will manage to flow through. For example, if there is no coffee at all, which is what it's like when I have all the possible edges to go through, this I should imagine as corresponding to P1, then I will be able to pour through completely. So I can imagine this as blocking. So every time I have a coffee here, a coffee bean here, it removes one of these possible edges of moving. And a lattice is an object that physicists really like because it's easy to work with. Okay, so this is just some motivation. And in this setting, on ZD, for example, it's very easy to show the following, that the following holds. So there is some critical point. So let me write it like this. Under P, so if I do P percolation, and I could write here ZD, but when the graph in question is obvious, I will just omit the subscript. So the probability that there exists an infinite cluster, infinite connected component. So are we all clear with what connected component means?
I think it's fine.
Yeah, so just in case not, then this is one connected component, another connected, etc. So the probability that there is an infinite component, so there is a phase transition in the sense that there is a critical probability which we denote by PC, such that this probability is 0 if P is below this critical probability, and 1 if P is above this critical probability. And this is a good point to mention, maybe, probably the biggest question in percolation theory. What happens exactly at PC? Is it 0 or 1? That's one of the, or probably is the greatest question in percolation theory. It is known in high dimension, where high means, I don't know, 16, 17 or so. Probably the methods can push it to 6, but solving it for Z3, for example, is completely wide open. But we're not going to focus exactly on PC. We're going to be interested in this critical probability and what we can say about it. Okay. And let me remain in ZD because ZD has drawn a lot of attention, and initially percolation was studied on ZD. So we had these two branches of things growing in parallel. We had the random graph community studying these things on the complete graph, and the percolation were studying it on ZD. So let me continue a bit the story on ZD. So what do we have? So we have, let's look at the parameter P. So we start at 0, we end at 1. This is the parameter P. And I just told you that in ZD there is some parameter PC. I don't care exactly what its critical parameter PC. I don't care what its value. And above it, you will have an infinite component, and below it not. So for example, let me draw it in a box. Although it's obviously it's something infinite. So below it, the image would be that everything is shattered. There is no infinite component. So all of these things that I'm drawing here are finite components. Each one of them is a finite component. But the image here above PC, as we said, is different. So we will have some, at least one infinite component. And there are other things which could be finite.
So I guess what you mean on this picture is that you take a large box,
Yes.
finite, and you see projection of your graph on
Yeah,
this.
and in ZD you can actually see it. But in general, you can imagine I just look at the, okay, in general, it's always true. If I look at a large enough ball, since ZD is transitive, I will eventually see the infinite component in it. Absolutely correct. Okay, and so this is the image that we have. And then a very natural question to ask is, so let me, a very natural question to ask is how sharp is this thing? How sharp is this phase transition? And we see this type of phase transition happening in many, many places. For example, consider water, right? Exactly the zero temperature. Below zero temperature, it's solid, and above it, it's liquid. Expansion of fire in a forest, explosions of diseases, etc. These things are very well known. So what do I mean by how sharp? So what we could hope is that, suppose I fix the graph ZD is transitive, which means that every vertex looks the same. So I can fix some point and call it the origin. So say this point here. It's the same as this point here. And this is the origin. And what would it mean for me that this transition is sharp? It would mean the following. So let's start with the subcritical regime that is below PC. So I would hope that maybe there is some point here, let's call it PC minus, such that if I'm below it, so this is the origin O, then not only that all the components are finite, but they are finite in a very strong sense. That is, the probability that, and let me write it like this, this is the component of the origin. The probability that the size of the component of the origin is at least n will decay very, very fast. So what is very, very fast? The best we can hope for is e to the minus cn. So obviously there is such PC minus, perhaps it's zero, but there is such PC minus where below it decays exponentially fast. And one of the first biggest results, so this is a theorem due to Eisenman, Barsky, from 87, and it was the Cold War, so also actually before them, he showed it. Shlikov in 86, if I'm not mistaken, says that for ZD, we're only talking about ZD right now, PC minus is exactly the same as PC. That is, the actual image is not what I drew here, but rather this is the same, and throughout this entire regime, we have this behavior. So long as I'm below the critical point PC, I have that, yeah, so just to be clear, obviously this is for every P which is below PC minus, this holds. Okay, so we know that at least in ZD, everywhere below the critical probability, we have this behavior, this exponential decay. Any questions?
Constant depends on PC.
Yeah, this exactly. Yeah, for every P bigger than PC, there exists a constant C which depends on P and on PC, such that for all n bigger than 1, we have this statement. Okay. Exactly. Thank you. So this is one part of the picture. Okay. So this is not here, but this is actually the same place. Okay. And then you can ask, okay, I have this very nice theorem. Can I find an analog of it for the supercritical regime? And it took some time, but not a lot of time, just a couple of years. And for ZD again, Grimet Marstrand in 1990, they showed that at least in the way that it is actually makes sense, PC is the same as PC plus. Now I haven't defined what PC plus is yet, so let me just quickly do that. So we have this image here. And now obviously it doesn't make sense to ask that the component is in a finite cluster because there is, when we're above the critical probability, there is a chance that it's in the infinite cluster. But what I can ask the following question. I can ask, what's the probability? And let me actually write the statement. So to be precise, for all P bigger than PC, there exists a C such that for all N, the probability under P that the cluster of the origin is finite, but has size at least N. So we want this to decay exponentially. Now the point is we cannot hope for it to decay exponentially in N for one simple reason. If you take a box, for example, in Z2, the number of edges going outside is not N, it's N to the D minus 1 over D. So whereas here in the subcritical regime, I do not even see the geometry of the graph. I see nothing. It's really almost just like it would look in a Galton-Watson tree, like I see absolutely nothing. Here, the geometry of the graph will have to take place. So actually, the right answer, and this is obviously tight, is that it's e to the minus c n, and then I have the isoperimetry. So d to the minus 1 over. So, and this is tight. It's easy to see it is tight. When I say easy to see, again, take a box, just force the box to be connected, and all the edges outside of this box to be closed, and you will get exactly this thing. It will cost you the same, so just a different constant. Any questions thus far?
So just we did not condition on the event that the connected component is finite, but we take an intersection or
Yeah, so this is an intersection. It's finite and it's of size at least. Sorry, at least 10.
at least.
Yeah.
So the
So what's the
probability.
Yeah, please go ahead.
So there is some. So the probability that C0 is finite is bounded away from 0, or I mean,
So
if I take.
Yeah, the moment that you are above PC, because the graph is transitive, every vertex looks the same. So the origin is, it could be in this infinite component. And this infinite component takes, there is some probability that it is connected to infinity, etc., etc. Yeah, and therefore it's bounded away from 0. It's also bounded away from 1. Yes.
Okay,
yes, exactly. So yeah, I actually didn't mean to write it, but one way to define this PC, and this is true here, but it's true also elsewhere. Maybe let me write it. One way to define it, and it's not hard to show these definitions are all equivalent. So I defined PC right before I said PC is the moment where there is an infinite connected component. But another way to define PC would be, so I can fix an origin, it's all the same. So it's the infimum over all probabilities such that the probability under P that 0 is connected to infinity, this is what the signs mean, is at least 0. So obviously if we are above PC, then the origin has a chance to be connected to infinity. And this is equivalent to the definition I said before. It's not trivial, but one can show it. I think it's in one of the notes of maybe Oded Shram that they are equivalent. He has a very elegant proof of this.
Connected to infinity means that zero lies in infinite component.
In an infinite
Right?
component, yes. Yes, this means that is in an infinite component, exactly. Okay, so thus far we talked about, first we took the view of our world, which is maybe for most of us the view of the world with complete graph and subgraphs. Now we looked at ZD, and let me now move to what we're actually going to talk about. And this is percolation beyond ZD. And this is actually a name of a paper by Bignamini and Schramm, where the actual title was Percolation Beyond ZD. Many questions, few or very few answers. So quite a nice title. And essentially what they asked there, so Bignamini and Schramm, they asked the following question in 1996. What happens if we replace ZD with some general infinite transitive graph? And you can ask, why would this be interesting? So this is interesting for several reasons. Well, first of all, there is a very deep theory developed for ZD. The question is, how universal is it? Is it universal for all, say, infinite transitive graphs? That's a very natural question just to begin with. But if for some reason you're a person who is very interested in lattices and only in lattices, perhaps asking and trying to understand what can be transferred to this type of setting will tell you what do you actually need from ZD for this property to hold. Maybe it will give you simpler proofs, and maybe it will tell you a bit more about what these things look like. So that's the first thing. But I think from the combinatorial point of view, this is very natural thing to ask immediately, even without the infinite transitive graph, but that's a nice starting point. And just to motivate you, so what are examples of infinite transitive graphs? So obviously we have the lattices, for example, ZD, but now we also have an infinite regular tree. But also any Cayley graph. With a finitely generated set of generator will give rise to an infinite transitive graph.
Yeah, sorry, Sahar, I missed the point where you recalled the definition of a transitive graphs.
And so a transitive graph is a graph where every vertex looks exactly the same. Formally, the automorphism, like you have an automorphism that maps every vertex to any other vertex that you want. It's vertex transitive.
Thanks.
Okay. So this is a much, much richer family of graphs, as you can see here. Okay. And it's still true here that you have this critical probability PC. It's not hard to show that this definition of PC, for example, also works here. Sometimes it could be perhaps that PC is just 1. It's easy to show it's bounded away from 0. Also, besides very particular cases, it is bounded away from 1, but this is quite this took some time to show. This was shown by Ugo de Minili Capone and co-authors, and there is also a nice new shorter proof by Philippe Isso, by Vincent Tassion, and by Franco. But that's beyond our scope. What we care about is the sharpness of this space transition. So I'm telling you, PC exists. PC exists, and pretty much for anything you care about, it's bounded away from 0 and 1. Unless you take a line, essentially, a torus, something that's really resembles Z. Okay, so what do we know here? So we know that subcritical sharpness still holds. And that apparently wasn't very hard to show. The same proofs given before for ZD generalize quite nicely to pretty much any infinite transitive graph. And in fact, there are by now modern simple proofs that even generalize to models beyond percolation, beyond the IID, Bernoulli P on the edges. So that was, to say, easy to achieve, easy to generalize. And again, this is 1996. And one of the big questions was, what about PC plus? So is supercritical sharpness still holds in this general setting? And there have been quite some work towards this. And again, what was known at least, are some nice non-trivial generalizations of the result of ZD. So there is a result for what is called that it is true. So let me say it like this. So it's true in these two particular cases. So first, if your graph is non-amenable, which just means, from our point of view, it's just an infinite expander. The Chigger constant is bounded away from 0. And you should remember all the graphs here it's a fixed graph. It's an infinite graph, but it's a fixed graph. So P is always a constant. And a non-amenable means that, and the degree is also constant because the graph is fixed. So non-amenable means that the Chigger constant is big. So this was shown in a very important work by Hermon and Hatchcroft in quite recently, if I'm not mistaken, in 2022. And this really relies on the fact that the graph is expander, first of all, but also on some geometric properties or things you can say the moment you know your transitive graph is non-amenable, it tells you something about it. And it was also shown for graphs with polynomial growth, transitive graphs, infinite transitive graphs with polynomial growth. So this means that if you take a ball and you start to grow it, it grows essentially like it would grow in a lattice, like according to some polynomial, not exponential and not anything bigger than polynomial. And this was shown by Contreras. Vincent Tassion and Martiniero.
This looks like opposite regime to be non-amenable, right? Because
Exactly. So these are the two
non-amenable-
extremes. These are the two extremes. So this is an expander, and this is very far from an expander. But here they use the facts it's an expander and also some geometric facts. This is exactly the other opposite part of the regime. Here what they use is they use a very important works of Gromov and Trofimov, which essentially tells you that while polynomial growth graphs are not ZD, that they're not a lattice where you can just, they don't necessarily have full self-symmetry. They are quasi-isometric to such graph. Like there is a very nice characterization, group characterizations of this graph. And using this thing plus some very cool ideas, they were able to show it for this family of graphs. Okay, and in this talk, what we'll talk about is our new result. So this is a result by Philip Isso. All the guys I'm saying here are from ETH, Ritvik, Ramanan, Radhakrishnan. Sorry. Benny Sudakov, Vincent Tassion, and myself. And it's already on archive. And what it says is that for any infinite transitive graph, the supercritical sharpness holds. That is, we have this exponential decay regardless of how the graph looks like. So let me maybe write it a bit more formally, what we mean here. So what we show is that, formally, and let me give two variants of this of the statements. One implies the other, but it's nice to see. With respect to what I showed before, I think it's important to see both of them. So we show that for every p which is above the critical probability, there exists a constant c, which could depend, as you said, on p and on pc. But remember, these things are constant, such that for every integer n, the probability under p percolation that the cluster of the origin is finite, but manages to reach quite a large size at least n, is at most exponential in some constant c, the same constant c that we said. And here I have phi of n. So what is phi of n? This is what we call the isoperimetric function. So I go, need to do infimum over all sets S of size at most, at least n, sorry, not at most n, at least n. At least n or at most n. You can do exactly equal to n, and that will also be okay. Of the number of edges, so this is the number of edges leaving the set. So I look at all sets of size n, and I take the one which minimizes this. For example, In the hypercube, this would be subcubes. If I look at ZD, then I can take boxes, etc., etc., etc. So this is just the minimum isoperimetry. So the difference between this and Chigger constant is just I don't normalize by the size of the set. It's the same as the Chigger constant without normalizing. And since supposedly I'm working with infinite graphs, I need to put here infimum instead of minimum. So this is the statement. Another way to formalize this, or actually a slightly stronger perhaps statement, is that the probability under P that we are in a finite cluster, but let me write it like this. Let me call it pi, which will denote a cut set, but I will tell you what it means exactly in a moment. Pi of C0 is at least n. This is at most exponential in minus Cn. Okay. Now, what is this? What is this pi? So for any fixed set S, so suppose I have some set S, it could be very wiggly. I look at the minimal cut set between S, edge cut set between S and infinity. So it's not necessarily the edge boundary of S, but there is some cut set here which separates S from infinity, and this would be pi of S. So formally, or slightly more formally, for any set S, pi of S is the size of the minimum edge cut set between S and infinity. And it's quite easy to see why this implies this, right? Because if pi of C0 is at least n, then phi of C0 is at least n, and we get exactly what we want. Or pi of 0 is, to be more precise, phi of n, pi of C0 is at most the size of phi of n. So there is a way to move between the two of them. And before we move forward, let me just mention that everything I said thus far is typed. In the sense that, just like in ZD, it's not very hard to show. Actually, it's more hard to show, but it's not very, very hard to show that there exists some C prime such that this is at most e to the minus C prime phi n. This is at most e to the minus, at least e to the minus C prime n. So we cannot hope for anything better. So let's pause on this for a moment because in the rest of the talk, the proof is quite simple in the sense that it doesn't use any heavy machinery, it's self-contained, and I hopefully will be able to present to you the entire proof, or at least the big ideas in the proof, and even save some time. So any questions about the statement itself?
No quasi-isometry and no group theory in the proof.
Nothing whatsoever. In fact, we barely use transitivity, and I will try to remember the only place we actually use transitivity and tell you what we can replace transitivity with. So the statement is in fact strong. But yeah, assuming transitivity is quite natural in percolation setting, and it works. Okay, very nice. So this is the theorem we want to prove. So yeah, let me maybe say, I'm going to prove this version implies the other. And of course, there are the quantifiers, supercritical, etc., etc., etc. And let me start by stating a proposition. And actually, the key part of our proof, argument, everything, is to actually prove the proposition I'm about to write. And deriving the theorem from the proposition, we will see it's quite simple. And in fact, the rough ideas of how to do it were known already before. So what's the key proposition? It says the following. So for every parameter, let's call it Q, which is bigger than PC, so supercritical. So you give me some supercritical parameter, then I'm able to give you some constants C and delta, both of them are positive, such that for every n, which is at least 1 for every integer, and for every finite set S with the minimal cut set between S and infinity being at least n, the probability under Q percolation that, and I will define what this means in a moment, the number of touches between S and infinity, I will define it more precisely in a moment, is large. So the probability that this happens is not too small. So say it's at least delta. Okay, so let's parse what this means in a moment for some drawing. So I have my my set S, which I fixed, and I have my cut set minimal cut set of S to infinity. So I have my pi of S. And what I'm interested about is the number of places, so that there are edges leaving S. And I want to count the number of places where I reach S and eventually I reach infinity. So for example, this is one touch, this is another touch, this is another touch, and these things, as I draw them, they reach infinity in some sense. So formally, I can write it like this. And when I say reach, I mean reach without going through S. So let me write it formally, where T of S is exactly the number of edges in the boundary of S, such that the edge eventually, this endpoint of the edge eventually, or is in an infinite component, but not using anything of S. This is okay as far as I'm concerned, so suppose I have this. This is okay, but I'm not allowed to do this. This is not good for me. I want it to go directly without going back to S. So this is a touch. And what I'm saying here is that the proposition will show is that it's not too unlikely to have quite a few touches. So if I know that the potential of touches, that if I look at like what I can enclose, the minimal thing I can enclose my set with and separate it from infinity. So say it says size at least n, and I fix this creature S inside, this set S inside, then if I'm supercritical, I will be able to move from S to infinity in quite a few points, and quite a few points with respect to how big this pi of S is. And maybe this is a good point because we have time just to say one thing here. Observe that it's quite easy now to see, believing me, or suppose you believe me, this is crucial. This statement is crucial. It's quite easy. Yeah.
Sorry. Again, pi of S counts edges as well, right? Or
Pi of
counts-
S is just edges. Yes.
But it's not edges that lead it to infinity.
No, these are the edges, the minimum cut set, the minimum edge cut set that separates S from infinity. It could be that some of them are in the boundary of S, and it could be that some of them are not in the boundary of S.
I see.
And
this here, you guys, here you count those guys that actually in the boundary, also separate
in
from
the
infinity,
also
but
in the boundary. In the boundary of S and eventually reach infinity.
I see.
So in particular, they cross this pi S, right? If I continue in Q percolation, this is done in Q percolation.
Transitivity is enough for it?
Yes.
And
Yes.
pi at S, is it in original graph or after percolation?
Yeah. Okay, this is very important. So let me do it like this. This is percolated. Blue is percolated. So this is after percolation. S is a deterministic set. These edges of the touching edges are not percolated whatsoever. I don't do percolation here. I do percolation only outside of S. And pi of S itself is a deterministic thing. So I look at the graph G, I look at the set S before percolation. I look at the graph G, I look at the set S, and I'm asking what's the minimal cut set between that and infinity. So this is indeed a deterministic thing. This is completely deterministic. Any more questions?
And G of S, the edges are also deterministic. It doesn't matter whether they survive the percolation.
Yeah, so it's a random object, but I don't consider percolation on them whatsoever. That's true.
So we see we consider all edges and as first step, and then we allow only edges that survive in the following.
Exactly. That if I look at their endpoint if I could mark them, but if I look at this thing here, this one, and I do Q percolation outside of S, I want it to belong to an infinite component.
Okay, thank you.
Of course. Great. And yeah, this is very related to what you asked and to what Maxim asked, to what you asked. And some point I wanted to make here is that observe that we can see, even with this very bad drawing that I do here, you can already see that pi of S is actually the right object to look at. Why? Because look at these edges here in what you can call I don't know, a fjord, something that enters here. These ones are kind of blocked by S itself. I could even make it a bit more narrower. So it's hard to imagine that they actually will do something very interesting. They're quite blocked. They're not going to give me a lot. What I actually care about is this isoperimetric optimal cut sets around. But we will make this all more formal in a moment. Okay, so this is the key proposition. And let me briefly show you how we can, let me make it a bit, okay, let me first write it. So I want to show you how we can prove the theorem given that we show the proposition. And again, showing the proposition is the hard part. What I'm showing you now, for example, it was known already before that if you show this with delta, then indeed it's possible. By example, there is a paper by Hatchcroft that shows some equivalences in a higher parameters, but never mind, the idea is essentially the same. So, okay, we can do it even formally, we have time. So let P, it's not the same P as in, so let P be a supercritical. And now I look at this proposition, and I want to apply this proposition to some. So let's say, let me be a bit precise. So let me pick some parameter Q, which is supercritical, but it is below P. I can do it. P is above PC, everything here is constant, so there is a space to put something in between them. So Q is supercritical, but below PC. So I pick it and apply the proposition to this Q. And if I apply to this Q, I get this C and delta. So now I have this C and delta, which ensure me this statement here. Okay. Now what do I want us to imagine? So remember that the theorem is that, let me scroll a bit up. The theorem is that the cluster of infinity, we're here, the cluster of infinity, sorry, the cluster of the origin is finite, but it has a large cut set. This is the what we want to estimate. Okay. And now I'm going to bound the probability of a certain event in two directions. So say I have the origin here, and I look at the cluster of the origin under P percolation. So this is the cluster of the origin under P percolation. It has some edges going out. All of these edges are closed. So this is in P percolation. And then, and trust me about this, what I'm saying now is legit. I'm not hiding anything. We can treat infinity as a point, a special point, but a point, and then the graph is just finite. So I have here infinity, it's a special point in the graph, and the graph is finite. A way to formalize it would be to say, okay, take large enough ball, and if I say explore something from infinity, I mean explore it from the ball, but forget about this for now. These are just really technicalities, it's used everywhere. So I have this point infinity, which I'm going to treat as a point, and I'm going to do Q percolation from this, from infinity. So I do some Q percolation, and I see, for example, it reached here, it reached here. So this is the infinite components under Q percolation. And what I want to estimate, so I want to estimate the probability that I see this image and the number of touches that I have here. So this is a touch as far as I'm concerned. This is a touch. This is a touch. This is a touch. So this is more than Cn. So I want to estimate the probability of this. This is the event I care about. Okay. So one bound is quite easy. Why is this event not likely? This event is not likely because here's a way I can imagine it. Imagine that I first start the percolation from Q, from infinity with Q, and I see that this is the image eventually. So this is what I got. Then I stop. Then I go to the origin. And now I do this percolation with parameter P. And I stop the moment I reach these edges of the touches. So I do this percolation. The percolation does whatever it wants. Eventually I reach these touches. And now, for this component to remain finite, for C0, for the component of the origin to remain finite, all of these edges have to be closed under P percolation, correct? Now, we have here CN edges, and we know that they are closed under Q percolation. So they are closed under Q percolation. But now I'm continuing this exploration with P, and I want them to remain closed. So they need to remain closed with P percolation. And this needs to happen to each and every one of them. So the probability of this event that I have the cluster of the origin explored in P percolation, touching the infinite component in CN places is extremely unlikely when I explore the infinite component in Q. It's extremely unlikely. Eventually it will penetrate through. Okay, this is on the one hand. On the other hand, let's use our proposition. So our proposition tells us that what's the probability that the number of touches is at least Cn? Well, this is at least delta. So I can pay this delta, the same delta, and ask that, let me make more space. I can pay this delta, and then just ask that under P percolation, C0 is finite, the cluster of 0 is finite, but this is at least 10. So I pay this delta to ensure that I actually have Cn touches, and then I just have this event here. So I can bound it from both sides. This is. Okay. But observe that this is exactly the event that we care. This is the event that we are interested in, the event that we have here. This is the event that we want to bound the probability of in the theorem. But we're in business because now we can rearrange and we get that the probability of the event that we actually care about, it's finite, but has a huge cut set, is at most 1 minus P to the 1 minus Q over minus 1 Q, Cn times delta, and this is exponential in Cn, which is exactly what we want. Any questions?
Could you repeat, please, the second equation?
Yes.
The
so
upper bound. What is the process?
This one or this one? The one in yellow?
No.
This one.
Yes.
Okay, so here I imagine this, in percolation, I can always imagine how I explore stuff. So imagine if this is the image that I see, I can imagine that I did it in 2 steps. First, I took infinity and I started to explore the infinite component. So, and I did it in Q percolation, and observe that Q is supercritical, but it's below P. It's smaller than P. And then I got this green picture. Then I'm done with the first step. The second step, I go to the origin, and now I explore it in P. Now, if this image is to occur, first of all, I will get exactly this thing, but when I reach these edges, these black edges, these touching edges, which I know there are at least Cn of them, all I know is that they are closed in Q percolation, right? I know this because I revealed the Q cluster of infinity and they were closed. Do you agree with me?
Yes. Okay.
Okay, but now if I want the cluster of the origin in P to have exactly this shape, these edges must remain closed in P. So you can imagine that I only reveal them in Q, and now I can sprinkle a little bit more probability to see whether they're still closed under P. And what is this sprinkling that I need to do? How much more probability can I add? How much more randomness do I have? So it's exactly this ratio. So the probability that it is closed, can say it like this. The probability that it is closed in P given that it is closed in Q, this is what you have here. 1 minus P is the probability it's closed in P. 1 minus Q is the probability it's closed in Q. I already know it's closed in Q. I want it to remain closed in P. And I need this to happen for every of these Cn edges, and this is all independent events.
When do we stop our first step of the process? Well, you want to go until you reach the cluster of the origin, but you still do not have the cluster of origin.
So I just reveal the entire cluster of infinity under Q percolation. I reveal the entire cluster of the origin under Q percolation. I do not stop. If it eventually reaches 0, then I'm done, because if it contains the origin, then the origin is an infinite component, and I don't care about this. This is not something I care about. Right? I only care if it didn't.
Right. Okay.
So I care here that the cluster is finite, and the cluster in P touches the cluster of infinity in Q in at least Cn places. This is the event I care about.
Yes, I think I understood. Thank you.
Okay, perfect. So now let me show you how we prove the proposition. Before I do that, let me just have one small remark. Observe here, and this is already one tiny novelty in our paper. Delta doesn't have to be constant. I can take delta, everything is okay. If delta is even something exponentially small, say 1 minus epsilon Cn, so long as 1 minus epsilon is, I just need to get my inequality right, is bigger. Yeah, obviously here it's divided by delta because I switch side. Is bigger than 1 minus p over 1 minus q. So I can even ask for this event to hold with a very small probability, exponentially small probability, but I need to be able to control this epsilon. Okay, so proposition star would be that the same thing, but with just, let me write it, proof of proposition star, and proposition star would be that for every Q which is supercritical, and for every epsilon, I'm not allowed to choose my epsilon. Epsilon is given to me. There exists some constant C such that for all n and for all S finite with pi at least n, the probability under Q that we have at least Cn touches is at least 1 minus epsilon Cn. So this is what we want to prove. and this will suffice, even though it's weaker than what we originally said. Okay, so how can we do this? So let me give you a 10-minute sketch of this thing. So let me start with some toy version, which doesn't work, but will give us the idea of what we want to do. I want to create these touches one by one. So I have my set S. And again, I'm treating infinity as a point. And as we said, we really don't need to worry about this. And if you remember what I defined as PC, we know that because we chose P to be, so if we're looking at something supercritical, so let's say peak P, we're given Q. So let me pick P to be between PC and Q. It's not the same P from the theorem. It's a different P. It's P just to prove this proposition. So if I pick such a P, then I know that the probability under P that the origin is connected to infinity is bounded away from 0 because it's supercritical. And I can call this, a standard notation is theta. Okay, so I have S, I have infinity, and observe that every point that I take, if I look at P percolation, so let me do it in blue, if I look at P percolation, it has chance at least theta to reach infinity. Now, it might happen in two ways. Either it reaches infinity immediately, or it goes through S and then eventually reaches infinity. But it's not really directed, but these are the two options. So every point has, by union bound, probability at least theta over 2 to go to infinity, and at least theta over 2 to first reach S before reaching infinity. So either to first reach infinity or first reach S. This is the property that we're interested in. And in particular, I can split my world. So things close to S will have higher chances to go to S.
You're saying
vice
that
versa.
one of these probabilities is at
Yeah.
least over 2, right?
Yeah, yeah, exactly. So this means I can split my entire world such that everything here has probability at least theta over 2 to hit S first, and everything here has probability at least theta over 2 to reach infinity first. And you know, this one, for example, neither side is empty. And the graph G transitive, blah, 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 it's connected. So there is an edge here such that this one goes first to S with probability theta over 2, and this one goes to infinity with probability theta over 2. So now, what I can do is I can ask, what's the probability that I have at least one touch under Q, under P? Under P, under Q doesn't matter here. Okay, well, I need to pay for this edge to be open in my P percolation. This costs me P. And then I need to pay for this to reach infinity in the P percolation.
Do you choose just any edge from?
Yeah, any edge, doesn't matter. Pick one. Assume they're ordered in some way. And this reaches here, and voila, I got a touch. So this times theta over 2 squared. And okay, suppose I did it once, then I can take another edge and keep doing this thing. And in general, there is a slight issue. So when I look at I can tell you about this issue. So when I look at the second edge, say this one, now it's not that it goes to infinity, but it's that, let me remove this. So when I reveal the P cluster here, so reveal this big cluster. It looks like this. So when I look at this edge, it's not that it goes to infinity, but that it goes to previously explored cluster of infinity. This is what I'm actually looking at. And this still will be theta over 2. So I can still pay theta over 2 in both directions. But now, so I will get a new touch, maybe even more than one. And it will reach this guy here. But this edge is P closed. And I want it to connect. So I need to add some sprinkling. So I need to pick some delta such that, say, P plus delta is less than Q. And then what I will have to do is I will have to pay delta to open this edge in an independent sprinkling. And then they merge. So in total, what I will get is that the probability under Q that T of S is at least some number T is at least, let me write it like this, P times theta over 2 squared times delta, all of this to T. For the first step, I don't need to pay this delta, but doesn't matter. Okay. Now, we want to replace these terms by 1 minus epsilon. We want to replace each of these terms by 1 minus epsilon. Now, as it turns out, it's the moment I will be able to replace these two terms with 1 minus epsilon, each one of them with 1 minus epsilon, I will be in business. This one will automatically reach 1 minus epsilon. It's not hard to show. If you have something that happens with high probability, it means that actually I don't touch in one place, I touch in many places, and then this delta will actually mean that I'm able to connect. I don't only have one edge, but I will have plenty of connections here, and it will be easier. Just trust me on this one. So the toy version is just to give you some vibe, and let me tell you how we actually do it. So I need to fix two things here. I want this P to become large, and I want this theta over 2 to become large, to become 1 minus epsilon. So here is one way to do it. So I have my set S, and I have infinity. And one thing that is true, since we are in a transitive graph, is that if we take a sufficiently large ball of sufficiently large radius, the probability that it reaches infinity in the entire graph is connected to infinity in the entire graph. You can choose it large enough such that this is 1 minus epsilon. So for large enough R, it will be 1 minus epsilon. And this is the only place we use transitivity. Any graph that you give me that satisfies this property, the proof will work for it. Okay. Great. So now I choose balls instead of points. So this allows me to fix this term to 1 minus epsilon. Now, how do I fix P? So in order to fix P, I need to take many balls, because observe that when I do this percolation, the fact that the ball itself is connected to infinity into S does not mean that it's in the same cluster. I would want the ball to be entirely open. Not necessarily entirely open, but it would be great if it's entirely open. So I need to take many such balls. And again, I can position them in such a way such that they connect to many places at the same time. So I take plenty such balls, such that, and I also need to take another sprinkling, but such that after I do this sprinkling, the probability, this one I tried, it wasn't fully open, I tried, it wasn't fully open, and then this one is fully open. So the probability that at least one of them is fully open is 1 minus epsilon. So I need to pay this 1 minus epsilon to open one of them. But once one of them is open, I will be able to reach, then I continue in the original percolation. This was in some small parameter percolation. And I will be able to get a new touch. And then I continue this thing. So this is another, say, 1 minus epsilon in order to ensure this new touch. And just one last thing to say. So, okay, this is great, but where does this pi come into play at all? So if you look at the first two example, you can see that pi actually doesn't come into play. So for example, I could continue until I saturated all the edges of S. If you think about it for a little bit, you can see this. And this tells you that this toy version is quite silly. But it's a good thing to start with, because when you move and you try to improve it, suddenly you see where phi comes into play, because I keep doing this process, and then I take, say, pulse here, pulse here, pulse here, and eventually I have something like this. So I have here touches, and here I have balls that some of them were great, but some of them are dead balls as far as I'm concerned. And observe, and I continue to have dead things here. And observe that when does this thing stop? It stops exactly when the number of touches plus all the dead balls form a cut set between S and the infinite cluster. This is exactly when it stops. So I can keep going. If I don't have a lot of touches, and I didn't run this too many times, I can keep going and keep finding new and new balls, so long as the minimal cut set is large enough. Because if the minimal cut set is large enough, I can keep finding these balls. This is exactly the point. If I don't have enough touches, and I didn't create enough touches yet, and I have any cut set between S and infinity is large, and I didn't run this process for long, because every time I run it, I'm able to create a new touch. I can keep adding new and new touches. Yeah. So let me stop here. Thank you very much for your attention.
Yeah, thank you very much, sir. Any questions? Right. So yeah, so you said this place where you essentially need transitivity, so you can probably formalize it. The conditions that you need instead of transitivity, I mean.
Yes.
Can you show that it is also necessary?
We believe it's not necessary. We believe that,
It's
okay,
not necessary for this proposition, or it's not necessary for the statement of theorem?
For the statement. We believe that, okay, we is a strong thing here, a large subset of the authors, of the co-authors, believe that the following is true. Take any connected graph you want, take it supercritical, you will have this supercritical sharpness. No assumption whatsoever.
Nothing except for connectivity?
Nothing except for connectivity, but observe that I'm asking you to be above this point
sure.
So the statement, if you, I don't even need it to be infinite. So for finite graphs, it would be that, okay, let me remain with infinite because it's easier. But the statement would be that the infimum over all pairs of points, the probability under P that U and V are connected is positive. We believe that if you have this as input, you will get as output this result. Some work in progress that we do now. So for example, we move to the setting of finite graphs or a sequence of finite graphs with growing degree. And then there is, then you need something else to replace this condition. But in general, we believe this to be true. Although this is a conjecture, we have no idea how to show it. We do know how to show it. So, yeah, just one more comment about it. What is quite fun is that if you think about finite graphs and the degree is growing, then we know to show that it's true under this very general hypothesis if P is some large enough constant times the critical probability. Now this makes sense if PC goes to 0. So when the degree grows to infinity in finite graphs, for example, this makes sense. So we know to show this under this setting. But and C is some constant. It's nothing that depends on the graph. So it would be very awkward if there are two phase transitions.
Minimal degree tends to infinity or what?
Yeah, I guess that's maybe what I want. Assume it's regular for now, but yeah, minimal degree I think is what I want to tend to infinity. In general, okay, to be precise, I just want the critical probability to tend to 0. I don't care what causes it. I could plant you some vertex of degree 1 and still the critical probability would go to 0. That's not the issue.
But this condition doesn't need anything. It doesn't need that critical probability tends to 0.
No.
Like less than
It just the fact that I know to show it with some constant here, it's meaningless if PC is half. If PC is half, then what does it mean to
constant is universal. It doesn't depend on the graph on anything.
On anything. It's like, I don't know, 10 to the 10 to the 10. It's actually much less, but I don't know.
I see.
Some large number. But it doesn't depend on anything. So yeah, even for graphs of bounded degree where PC is 1 over a trillion, then it starts to make sense. But in general, it doesn't necessarily make sense.
Yeah, very interesting.
Yeah, this is not published anywhere. But it's similar to what we do here.
Thank you, Sahar. Any other questions?
You started with deriving your theorem from the proposition, and you say that it is something well known. So this proposition should be something standard, and maybe it is interesting without connection to the further proof, and then you prove a relaxed version. So what is about original proposition? Is it do you know whether it holds with constant delta?
Yeah, the moment you have supercritical sharpness, which is what we proved, you automatically get this you can use some expectation type arguments, and this proposition itself is true.
All right, so thanks, Sahar, very much. It was a pleasure to have you and very nice talk and great result, of course.
Thank you very much. Thank you for having me.